Hello, I'm Dr. Sigarkanti. In this video, we define analytic function and the necessary condition for a function to be analytic. Before going to that, first we define complex valued function. So that is here. Let Z be a complex variable. So that is Z is equal to x plus I into y. And let f of z be a function of z. Be a function of z, then f of z is a valued function. Complex valued function. So that is f of z must be of the form u of x comma y plus I into v of x comma y. Or simply we write this as u plus ib, where u and v are functions of x and y. This is a complex valued function. Now here a function, I will define the analytic function. That a function f of z is said to be analytic at a point, say z naught. At a point, say z naught, if f of z is differentiable at z naught, and also at every point in some neighborhood of z naught. So that is, see, this is the point z naught. This is the point z naught, and this is some neighborhood here. Okay, this is some neighborhood. If the function is differentiable at this point z naught, and also at every point in this neighborhood, in this circle, okay, then we say that the function is analytic. Okay, that is, the function f of z is said to be analytic at a point z naught if it is differentiable at z naught and also differentiable at each point in some neighborhood of z naught. Then we say that the function is analytic at the point z naught. And suppose this is the domain D. Okay, this is the domain D. That means this is consisting of some points here. Then you say that the function is analytic in D if it is analytic at every point of this D. So that is, suppose this is the point Z naught, this is the point Z1, this is the point Z2, this is the point Z3, Z4, Z, like this. So that function is analytic at z naught, analytic at z1, analytic at z2, analytic at z3, like this. So that is, if it is analytic at all the points in this domain, then you say that the function is analytic in the domain D. Now we'll go for the necessary condition. I'll go for the necessary condition for a function to be analytic. That is here. Before going to that, we define Cauchy-Riemann. Cauchy-Riemann equations. Cauchy-Riemann, or simply we write CR equations. What are CR equations? If f of z is equal to u plus iv is a complex valued function, then the equations w by x is equal to w by y, and w by y equal to minus w by x. These two equations are known as Cauchy-Riemann equations, that is CR equations. Now we'll go to the theorem, necessary condition. Theorem, necessary condition for a function f of z to be analytic. The statement is if a function f of z is equal to u plus iv is analytic in a domain say D, in a domain D, then the partial derivatives ux uy, that is w by x, w by y, and vx vy, w by x and w by y exist, and satisfy CR equations. This is the necessary condition. So that if the function f of z is analytic in a domain D, then all the four partial derivatives exist and they satisfy CR equation. That is w by x equal to w by y, and w by y equal to minus w by x. Okay. So what we need to do is to prove this theorem. First I will consider the function f of z is analytic. Then I will try to show that the partial derivatives exist and they satisfy the CR equations. Okay. So I'll go to the proof. Let f of z be analytic in a domain D. Then f of z is differentiable in D, because it is analytic, it is differentiable. So that is f dash z exists. F dash of z exists. And here we have f dash of z is equal to limit, this is by the definition, delta z tends to 0, delta z tends to 0, f of z plus delta z minus f of z divided by delta z. And here we have as z is equal to x plus iy, therefore delta z equal to delta x plus I into delta y. Delta x is change in x, delta y is change in y, and delta z is change in z. Now here this is equal to limit delta z means delta x plus I into delta y. This tends to 0. What is f of z plus delta z? We have, see here, f of z is equal to u plus iv, right? U plus iv. That is u of x comma y plus I into v of x comma y. Then what is f of z plus delta z? This is our u x plus delta x comma y plus delta y plus I into v of x plus delta x comma y plus delta y. This is our f of z plus delta z minus f of z. F of z is u of x comma y, u of x comma y plus I into v of x comma y. This divided by delta x plus I into delta y. I will take this as a 1. This is the relation 1. Now here, if delta z is purely real, what this implies, if it's purely real means delta y, there is no imaginary term. Delta y is equal to 0. Okay, delta y equal to 0. Therefore, f dash of z is equal to limit delta x tends to 0, u of x plus delta x comma y plus I into v of x plus delta x comma y, because delta y equal to 0, minus u of x comma y plus I into v of x comma y, this divided by delta x. And I will write this as, this is equal to limit delta x tends to 0. First I will write this term, u of x plus delta x comma y minus, then I will write this term, u of x comma y, u of x comma y, okay. I will take the separate denominator, this divided by delta x, then I will consider this term, I into v plus delta x comma y plus I into v of x plus delta x comma y plus or minus this term, I into v of x comma y. So I have written I here, okay. This is equal to v of x comma y, this divided by delta x. See here, this one, this is the difference of u. Here, the change is in only x, not in y. So here y is fixed here. So that means here, this is our u of x plus delta x comma y minus u of x comma y divided by delta x, as delta x tends to 0. That means this is nothing but the derivative of u with respect to x, treating y as constant quantity. We have kept y as a constant quantity. Means this is nothing but dou u by dou x plus I into See here, v of x plus delta x comma y minus v of x comma y divided by delta x. Limit of this. So here y is a constant quantity. There is change in x here. Okay. So v of x plus delta x comma y minus v of x plus delta v of x comma y divided by delta x. This is nothing but differentiation of v with respect to x, treating y as a constant quantity. So that means this is nothing but dou v by dou x. I will take this as relation number 2. Okay. I will take this as relation number 2. Next, if delta z is purely, imaginary, that is delta z is equal to I into delta y. So that is here delta x is equal to 0. Then this relation 1 becomes this relation. So here we take delta x equal to 0 means this is u of x comma y plus delta y. Okay. I into v of x comma y plus delta y. This is u of x comma y plus I into v of I into v of x comma y divided by in the denominator v as delta x is equal to 0. This denominator becomes I into delta y. So therefore 1 becomes, so from 1 implies f dash of z is equal to limit delta y tends to 0. Delta y tends to 0. That is delta z tends to 0 means I into delta y tends to 0. I into delta y tends to 0 means delta y tends to 0. Then we write this one u of x comma y plus delta y. Okay. There is change in y. The delta x is equal to 0. So that is here we write this as u of x comma y plus delta y plus I into v of x comma y plus delta y minus u of x comma y plus I into v of x comma y, this divided by I into delta y. Delta z, we have taken delta z equal to I into delta y. And I will write this as this is equal to limit delta y tends to 0. I will write this as u of x comma y plus delta y. I will take this term here minus I will take this term u of x comma y minus u of x comma y divided by I into delta y plus I will take the separate denominator. Next I will take this term here. This term that is here I into v of x comma y plus delta y. V of x comma y plus delta y minus, I write this term here, minus I common factor here, I have written this outside, v of x comma y. V of x comma y divided by I into delta y. So here in this case, I gets cancelled here. Okay, I will cancel this I and I. Now this is equal to, that is here left hand side is f dash of z is equal to, see here this term. There is a change in y. Here we have y plus delta y, here we have y. There is no change in x. This is nothing but differentiation of u with respect to y, treating x as constant quantity. That means that this is dou u by dou y. So 1 by I is here, dou u by dou y plus here I gets cancelled. V of x comma y plus delta y minus v of x comma y. There is change in y, not in x. We are keeping x as a constant quantity. Therefore, this is nothing but differentiation of v with respect to y. That is dou v by dou y. This is our dou v by dou y, or we write this is equal to, so here I will multiply by I, divide this by I. If I multiply by this by I will get I. In the denominator I square is nothing but minus 1 into dou u by dou y plus, I'll keep this as it is, dou v by dou y. Or we write this is equal to dou v by dou y minus I into dou u by dou y. So this is, I'll take this as relation number 3. See here, what is relation number 2? Relation number 2 is this one. F dash of z is equal to dou u by dou x plus I into dou v by dou x. This is the value of f dash z. And here in 3 we have, this is also f dash z. That means LHS of 2 and 3 are same. Therefore, RHS must be same. So that is we write here from 2 and 3, we write RHS of 2. RHS of 2 is dou u by dou x plus I into dou v by dou x. Dou u by dou x, dou u by dou x plus I into dou v by dou x. This is equal to RHS of 3 is dou v by dou y minus I into dou u by dou y. Okay. Now comparing these two are equal. Therefore, real part must be equal to real part. Imaginary part must be equal to imaginary part. So that is, this implies, what is real part here? On the left hand side, dou u by dou x is equal to. What is the real part? On the right hand side, this is dou v by dou y. Dou v by dou y. And what is the imaginary part on the left hand side? This is dou v by dou x. Dou v by dou x is equal to, what is the imaginary part on the right hand side? Minus dou u by dou y. Minus dou u by dou y. So that is dou u by dou x is equal to dou v by dou y, and dou u by dou y equal to minus dou v by dou x. Dou u by dou y is equal to minus dou v by dou x. So these are nothing but CR equations. So that is here, if the function f of z is analytic, then they satisfy, the partial derivatives satisfy CR equation. This is the necessary condition for a function to be analytic. Okay, thank you. I will stop here.